So we know that in measure theory and probability theory, set theory is a very basis based on which everything is built. So we have discussed many things about set theory, and based on that some sigma field, how we can define measure, all these things. And also when we define a measure space, we know that there is something called measurable function. So measurability is very important thing, and whether a set is measurable, whether a function is measurable. And when we have studied sets, we know that we have studied sequence of sets, and whenever we say sequence of sets, we can think of its limit, and we have seen that there are some concepts like lim-inf and lim-sup, all these things are there. So today what I thought that I should discuss a few problems on this set theory, which is related to set theory or the sequence of sets, maybe involving lim-inf, lim-sup, etc. And when we define a measure space, we will discuss a few problems on measurable functions. So that is what we are going to do today. We are going to discuss probably 4 problems if we have sufficient time, and we will discuss 3-4 interesting problems on set theory and measurable functions. So the problems that I am going to consider today are from different topics in probability and measure theory. So basic objectives is to first discuss a few problems on set theory, which is the basis of measure theory and probability theory, and also a few problems on measurable functions. So the first problem is based on the set theory or the algebras. So if we have an increasing sequence of algebras, that is script an, n belongs to the set of natural numbers, that means script a1, script a2 and so on, and this sequence of algebras are from subsets of a set omega, then we have to show that union of an is also an algebra of subsets of omega. This is first problem, and another problem is that this implies that union of a sequence of algebras of subsets from a set omega is also an algebra. But is it true that if an is in the above problem is a sigma algebra instead of simple algebra, for every n belongs to the set of natural numbers, the union is also a sigma algebra. So we will discuss these 2 problems first. Now to solve this first one, let us first denote script a as union of n belongs to the set of natural numbers. Now to show that script a is an algebra, we have to check the 3 conditions that are necessary for a set to be an algebra. The first one is, note that each an is generated from omega. That means it naturally implies that big omega belongs to script a n for every n. Every n belongs to the set of natural numbers. And so naturally omega belongs to the union of n's, and hence we can immediately say that omega belongs to script a. The second one is for the complementation. So let's take any element a, that means any set capital A belongs to script a, then we can immediately write capital A belongs to script a n for some n belongs to the set of natural numbers, which immediately implies a complement belongs to script a n because a n itself is an algebra. So it is closed under complementation. And since this holds for some n, then naturally a complement belongs to union of script a n, that is a. So the 2 conditions are proved. We are only left with the third one. So let us consider 2 sets a and b belongs to the algebra script a, which is the union of a sequence of algebras. Now it is enough to show that it is a union b belongs to script a, that is, it is closed under union. Now note that an is an increasing sequence. That means a1, script a1 is a subset of script a2 and so on, and ab belongs to script a of union of script a n. So there exists always an n naught such that AB belongs to script A naught. So then immediately, since A naught again is a sigma algebra, we can immediately write A union B belongs to script A naught, which means A union B belongs to script A. So we have proved that if we take two sets A and B from script A, that is union of script A n, then A union B belongs to script A. That means it is closed under union. So these three properties are satisfied. So we can immediately say that script A is an algebra. Now, to investigate the second one, that means whether this is true for sigma algebra, first note that here we are now going to deal with sigma algebra, which is slightly different from a simple algebra, and naturally we can expect that these two things, that is sigma algebra and algebra, might show some different things in different perspectives. So let us consider a big omega as the set of natural numbers and an as a family of all subsets of 1 to up to n, that is the first n natural numbers and their complements. So this is our an, script an. Now if n varies, then naturally we will get a sequence of such sets or algebras. It is clear that script an is a sigma algebra. We can easily prove it. And also it is immediately obvious that script A1 is a subset of script A2 and so on. But if we look at the union of script An, when n belongs to the set of natural numbers, this union is a family of all finite and cofinite subsets of set of natural numbers. And naturally this cannot be a sigma algebra. So basically the converse, that means B part, is not true. So this is an example which shows that B part is really not true. So what is true for algebra, that might not be true for sigma algebra. So this gives us a nice idea about what is going on inside sigma algebra and what are the conditions that we need to check in order to see whether we can have a sigma algebra or an algebra. Now we move on to the second problem, which is based on a measurable real-valued function. So let us consider f as a measurable real-valued function and g is a continuous function defined on the set of real numbers, that is R. Then we have to show that g composition f is also measurable. So this is one problem. Exactly the same line we can think of another measurable problem on measurable functions, like if f is measurable, then show that modulus of f is also measurable. But again we need to see, it is very interesting to observe that whether the converse of this problem is true. That is, if mod f is measurable, then can we say f is measurable? So we will discuss these problems one by one. So first one, let us take any real number alpha, that alpha belongs to R. Then the set of x's such that g composition f of x greater than alpha. So we are interested in the set of numbers x such that g composition f, so this is a function of x greater than alpha. That means for what values of x this g composition f will be greater than alpha. Now this entire set, this is a set. This can be easily written as g composition f inverse of alpha to infinity. Now we can immediately write this thing as f inverse g inverse of alpha to infinity. Now remember, g is continuous, so g inverse alpha to infinity, this open set of, and if you take g inverse, is also an open set, and hence it is a Borel set. Now since this is a Borel set, then we also know that f is measurable. That means f inverse of this Borel set, that means this thing must belong to the sigma field, underlying sigma field, based on which we are actually discussing this measurability. So since we know that f is measurable implies f inverse of that Borel set, that inverse image, also belong to a sigma field, then we can immediately say that g composition f is also measurable, because from the second line we observe that the right hand side basically indicates that this entire quantity belongs to the sigma field, and hence we can immediately say that G composition F is measurable. So the technique is that only to look at the inverse image. So that's the only technique we have used, and of course the continuity of the function G. The second problem is related to mod F. So that means we have to work with the mod function, modulus function. So the simplest way, and if we want to draw some link from the first problem, that is to A, we can take, if we take GU equals to mod U, then G is again continuous. Now since G is continuous and we know that F is measurable, so by the previous problem, G composition F of X of course is measurable, which is G of Fx. Now G of Fx is again mod of Fx. Hence by part A, mod F is measurable because we have already proved that G composition F of X is measurable when G is continuous and F is measurable. So mod F is measurable when F is measurable. Now we want to see whether the converse is true. That means if mod F is measurable, then can we always say that F is measurable? Unfortunately, the converse is not true. So all we have to give one counter example. So let E be a non-measurable subset of R. So note this significant term, non-measurable. Now consider a function fx which takes the value 1 if x belongs to E. E is a non-measurable subset of R, and minus 1 if x doesn't belong to E. Then it is obvious that if we consider f inverse of the interval half to infinity, that means consider an interval half to infinity and consider the inverse image that with respect to f, that is f inverse of a half to infinity open interval. Now this entire thing is nothing but E, but we are given that E is not measurable. Again, if we look at the interval half to infinity, that means this is an open interval, that means this is an open set. So F is actually not measurable. It's clear that F is not measurable because the inverse image we get is E, which is not measurable. But if you look at mod F is always 1, and of course this is measurable. So this gives a nice counter example that mod F is measurable, but F may not be measurable. So we have some idea about the measurability of a function, when a function can be measurable, and we can have many other problems with respect to this property of a function. That means whether it is measurable or not. Next problem is again related to the measurable function. Let Fn, n belongs to script n, be a sequence of real-world measurable functions, and F is another extended real-world measurable functions on a measurable set D. Now D is a subset of R such that limit Fn, n goes to infinity, equals to F. That means we have a sequence of extended real-world measurable function and another extended real-world measurable function, of course on a particular measurable set D, which is a subset of R, such that the limit exists. That means limit of Fn exists, which is equals to F on D. Then for every alpha belongs to R, there is a real line, we have to show that mu of the set x belongs to D, fx greater than alpha is less than equals to liminf, as n goes to infinity, mu of x belongs to D, fn x greater than equals to alpha. And the second part is more or less same, that is mu of x belongs to D, fx less than alpha, less than equals to limit n goes to infinity, mu of x belongs to D, fn x less than equals to alpha. Now actually we are going to prove one of these two because the other one will follow the same logic. So let's concentrate on part A. But before that, let us first recall a few definitions. So for any sequence of measurable sets En, n belongs to the set of natural numbers, we know that mu of liminf En is less than equals to liminf n goes to infinity, mu of En. And what is liminf of En? Liminf of En as n goes to infinity is union n belongs to the set of natural numbers, then intersection k greater than equals to n ek. which is equals to limit n goes to infinity ek in union of intersection of ek k greater than equals to n. Now this can be proved very easily. I am not going to elaborate the proof of this, but let us concentrate on the problem that we are going to discuss. We have just considered. So for every alpha belongs to R, let us define ek as x belongs as a set such that x belongs to D if kx greater than equals to alpha. This equality is very important. For each k belongs to n, that is the set of natural numbers. So remember the way we define ek and also the definitions, right? What happens to mu of lim inf en and what is lim inf of en. So lim inf of n goes to infinity equals to limit n goes to infinity intersection ek k greater than equals to n. Now we can immediately write this thing as limit n goes to infinity of x belongs to D if k x greater than equals to alpha, intersection of that. Now as n goes to infinity, we will immediately have that x belongs to D f of x greater than alpha, since f kx goes to fx on D. That is given actually. We know that the limit exists. So using 1, we can immediately write mu of x belongs to D fx greater than alpha is nothing but mu of lim inf n goes to infinity x belongs to D fn greater than equals to alpha, which is less than equals to lim inf mu of x belongs to D fn greater than equals to alpha. So we can take this lim inf outside mu, but there should be an inequality sign here, and that's the proof actually. So the second inequality should follow using exactly the same argument. So we are not going to write down this entire second proof of the part B, which is exactly in the same way. So let us now move on to another interesting problem with respect to measure space. So let omega script a and mu be a measure space, and let f be a bounded real valued a measurable function on D. D is a subset of script a. Script is a sigma field generated by the class of subsets of omega such that mu of D less than infinity. Now also suppose that mod of fx less than equals to m for x belongs to D for some constant m greater than 0. Then show that we have to show two things. One is if integral f d mu over D equals to m into mu D, then f equals to capital M almost everywhere on D, and if f less than m almost surely on D, and if mu D greater than 0, then integral f d mu over D is less than m mu D. So these are the two things that we are going to prove. The first, consider exactly in the same way as in the preceding problem. First, consider a sequence of sets En which is equals to x belongs to D such that fx less than m minus 1 by n for every n belongs to the set of natural numbers. Then noting the fact that f less than equals to capital M on D minus en, it can be easily shown that we have integral over D f d mu. We can split this thing into integral over en f d mu plus integral over D minus en f d mu. Now naturally the first integral, from the condition, from the way we define the set En, we can immediately replace this f by m minus 1 by n. So we get this first line equals to less than equals to m minus 1 by n into mu of en, plus second quantity is nothing but from the definition of f d mu, that is m into mu of D minus en. So all we have to evaluate what is actually mu of D minus mu n, and then probably the proof will be complete. So since En is a subset of Dn and mu D is less than infinity, we can always prove that mu of D minus En equals to mu of D minus mu of En. So again, from the previous result we get integral over d f d mu less than equals to m minus 1 by n mu en plus we had initially m into mu of d minus en, then now we have m into mu d minus m into mu en, and just a little simplification will give us which is equals to m into mu d minus 1 by n mu en. But by your assumption, there is a given condition that integral over d f d mu equals to m into mu d. Hence, we have integral over d f d mu which is less than equals to m minus 1 by n mu en plus m into mu d minus m into mu en, which simplifies to m into mu d minus 1 by n into mu en. Now, it is given that integral over d f d mu equals to m into mu d. So, if we put this thing in the left hand side of equation 1, we get 0 less than equals to minus 1 by n mu en less than equals to 0 for all n, for every n belongs to the set of natural numbers, which naturally implies mu of en equals to 0. Now, clearly union of n equals to 1 to infinity is nothing but x belongs to d such that fx less than m, which we call e. Therefore, 0 less than equals to mu of e. Now, e is the union of en, so it is again less than equals to summation n equals to 1 to infinity mu of en. That is the property of a measure which is equals to 0. We have just proved it, that mu en 0 for every n. We have proved it, mu en equals to 0 for every n. So, we get mu e equals to 0. Now, that means again we know that modulus of f less than equals to m. So, equation 3 implies that f equals to capital M almost everywhere on D. That is the proof of the first part. Now, the second part follows similarly. Note that integral over df d mu is less than equals to m mu d because mod of f is less than equals to m on D. Then we have to show only that the strict inequality holds, because this part is obvious, it is either less or equal to m, but we have to show that it is less than m. So, the strict inequality part. So, if possible, we assume that integral over df d mu equals to m into mu d under this condition. Then by part A, we can immediately write that f equals to capital M almost everywhere on capital D. But again, this contradicts the fact that f is less than capital M almost everywhere on D. That is a given condition. So, our supposition is wrong, and that means we only have integral over d f d mu which is less than m into mu d. So, we have discussed 4 problems on set theory and measurable functions. It is interesting to see that we have applied different theorems, different ideas, different concepts and results in order to prove whether a function is measurable or not, or when a function can be measurable based on some different, or rather when we define a new function based on 2 other functions, under what conditions that new function will be measurable for a particular problem. So we can explore different other problems in this area with the same notion, same logic, and most importantly the techniques that we have used in solving those 4 problems. So that is the most important message that I would like to convey through these problems.